So our next speaker is Christian Spiering, and he will, from Daisy Teuten, he will talk about high energy neutrinos and the neutrino telescopes, please.
Okay. So again, as nearly everybody else, I want to thank the organizers to be invited to this interesting symposium. And I will speak about the field which I'm working in since 30 years, neutrino astronomy and neutrino telescopes. And let me start with a synoptic view of neutrinos around us. Of course, you have here the cosmological neutrinos, which have just been discussed in the previous talk, and then the solar neutrinos, supernova neutrinos, 87 reactor neutrinos. Of course, that depends where you are on the Earth. Terrestrial neutrinos, atmospheric, astrophysical, and here at the end, the Berezinski-Zatsepin or GZK neutrinos. And if you look to the detection possibilities, then you see this is a domain of underground detectors. If you go to higher energies, then you need bigger detectors in open water or open ice. And if you go to even higher energies, it's radio detection, acoustic detection, or detection with the help of air showers. And I will focus to this part only. I will not speak about underground, not to speak about radio detectors, not speak about the attempts to build surface detectors, only about the deep water, deep ice detectors. The principle was, as you have heard already several times, it was proposed by Markov in 1960, where he said we propose setting up detectors deep in the lake or in the ocean to determine the direction of charged particles with the help of the Cherenkov radiation. We consider mu mesons produced in the ground layers under the detector. And this is exactly what you see here. An upward moving muon neutrino makes an interaction. The muon carries this cone of Cherenkov light, and from the arrival times you can determine the direction. At the arrival times at different space points you can determine the direction, and from the amount of light you can estimate the muon energy. So actually this idea was dormant for something like a dozen of years, and it came to life in the context of a problem which appeared in an underground detector. You have heard in the talk by Paolo Lipari that there was this Utah salt mine detector, and they observed the muon intensity, downgoing muon intensity as a function of the zenith angle, and they saw some inconsistencies. And to resolve them, they said, okay, we better take a medium which is homogeneous, not earth or salt or something like that, and which has a flat surface. And that, of course, was ocean. And in that context, in '93, so I'm following in much of what I tell here about Dumont, Robert's Birth of High Energy Neutrino Astronomy, a personal history of the Dumont project from 1992. So these people met at the ICRC and discussed how to solve this puzzle with the muon depth intensity curve, Keufel effect. The Keufel was a member of that collaboration. And these puzzles then faded away, but of course there remained the awareness that such a detector could serve as a neutrino detector. And the name was easily found, Deep Underwater Muon and Neutrino Detector, proposed by Fred Reines, and that stands behind Dumont. Then there was a first workshop in '79, and then soon a Dumont steering committee was formed, chaired by Fred Reines, John Lernand, and Arthur Roberts. Well, the question was which physics? And actually there have been three lines of thinking. The first was the underwater neutrino detection of interstellar neutrino emission, that means supernova neutrino and things like that. And it's clear that's very rarely, the energies are very low, so you would better move that to other detectors, in that case IMB. Athena was focusing to atmospheric neutrinos, and again it was easily realized that this also goes, at least if we speak about low energy atmospheric neutrinos, that goes better to underground experiments. And the final focus was then of a detector which focused to the very high energies, say 100 GeV or TeV or higher. That was a preferred option, but nobody really knew the fluxes. And Arthur Roberts was the first Dumont conference in '75, found the conferees unsure how big a detector should be for high-energy neutrinos and of what its astrophysical objectives might be. It was not until the 1976 conference that this aim crystallized. So the way how neutrinos are produced is in principle easy. The flux is not clear. So the way is, of course, you have a proton which is somewhere accelerated. You have a target. You generate neutrinos via this chain, and this, of course, gives you the ratio of electron to muon to tau neutrinos 1 to 2 to 0, which was the assumption until the early 90s, or even mid of the 90s, when people started to really believe in oscillations, and then it became clear that the ratio should be 1 to 1 to 1. But all the earlier flux measurements assumed this here, the earlier event number calculations assumed this here. I should say there are also other scenarios. You could, for instance, assume that the matter is so dense that the muons have no time to decay, and then you have only muon neutrinos. Or you could assume that the particle which escapes are neutrons, and then the neutrons decay, and you have only electron neutrinos. But this is a standard assumption. And of course, the neutrino is not necessarily to be generated in the source, but it could also be generated on the way by scattering at the background radiation. And these are this process was first proposed by Greisen, Zatsepin, Kuzmin, but the flux of neutrinos was first calculated by Berezinski and Zatsepin in 4 years later. And it's very hard to extract a clear number from these calculations, but it is about 1 event per cubic kilometer. This was not the benchmark for the people designing Dumant, but this, of course, is interesting to keep in mind if we speak about first Dumant proposal and about IceCube. So there have been a lot of Dumant workshops, and I have to say we are just digitizing them and want to put them on the web. And again, I see that's an unbelievable source of ideas. Some of them are, of course, crazy. And if today a PhD student comes with a new idea, you can practically always say you are reinventing the wheel. The idea is already in these proceedings. Of course, the means to realize the goal are today much, much better than at that time. So here you see the different workshops. By the way, this is here a misprint. Of course, this should be, John, this should be 80 or 81 or 82 or so. 80, yeah. So, of course, as I said, the principle how these particles are generated have been known, but how AGNs, radio galaxy, pulsars, binary system, galactic center, cocoon sources, where only neutrinos escape and no gamma rays and no cosmic rays, that was all at that time still rather speculative. One thing which I want to mention is the Glashow resonance, which Glashow proposed in 1960 already, and then Berezinski and Kazizov in 77 calculated where this resonance would be in this process if the electron would be in rest, and you arrive at an energy of 6.3 PeV. That is something which also has been discussed in the early Dumant proceedings, and that's, by the way, the only way to distinguish neutrino and anti-neutrino. And actually, I think, Francis, you will that also show later, we have a first candidate for that. Energy here is a little bit less than 6 PeV, but that has to do with not full containment and for some hadronic losses. So after such a long time, we have now the first result here. This is a first Dumant design. It's 1.26 cubic kilometer from 1978, more than 20,000 optical modules. And of course, it was clear that this will face some technological and financial challenges. And Roberts writes, the oceanographers were amazed this project was larger than any other peacetime ocean project by a factor of the order of 100. The size of the array was based on relatively scant information on the expected neutrino intensities and was difficult to justify in detail. The general idea was that neutrino cross-sections are small and high-energy neutrinos are scarce, so the detector had to be large. So this is now the actual development. This was the original idea. Then 80, that was already a bit smaller, only 6,000 optical modules. 82, it was reduced to 700 optical modules. And this what came out in 88, a detector of 216 optical modules, 250 meters high, 100 meter in diameter. And so that's about an eighth of the Amanda geometrical volume. And so then there was a very strong activity in the 80s with cruises, with research vessels, where strings were deployed. 2 of them were lost in some of these cruises. But in 87, there was finally success with a 7 optical module string. The depth intensity curve could be measured. And now really at different depths, not just as in zenith angle dependence. Angular distribution also, and the attenuation length was also rather encouraging, namely 47 meters. Of course, oceanographers had measured that with their own methods before, but this was a confirmation with the help of this string. So what then followed was that HIPAP supports DUMAN2, that this array was called DUMAN2 with the 8 strings and 216 modules. Then DOE allocated funds, further financial cuts led to a 3-string version, and 3 strings is the minimum you need for a 3-dimensional reconstruction, of course. 1993, a cable was laid to shore. Then a first string was deployed, but it failed after several hours. Actually, the data taking time was even less. And there was much hope that it was retrieved, but much hope that it could be deployed again. But finally, 1995, the project was terminated. And I think John can comment that later, what was the reasons. I mean, I heard the end of the Cold War and the availability of underwater equipment played a role, of course. Several failures played a role, and maybe even the appearance of Amanda played a role in that. I don't know.
The failure of the SEC.
And the failure, yeah. So one thing which I also want to mention, which still appeared before the termination of DUMAN, are these double bang events which have been proposed by John and by Sandeep Pakwasa, where you have a clear signature for nu tau. You have here a tau neutrino interaction, and then at a very high energy, the tau travels long enough, so and decays here. And so you have here first a hadronic cascade, and here a second hadronic cascade. And actually, even for that, we have now good candidates just this year. You see here a double bang event, which is not so clearly to be seen from here. The fit gives here 2 bangs. And if you look to the single optical modules, you see here this double pulse structure. And so this is at least a good candidate. I would not like to say it's a clear double bang event, but a good candidate. So now about Russia. The Russians have been very active at all these DUMAN workshops, and finally they were kicked out after the Russian-Afghanistan invasion. And I always like to cite Roberts, who write, Russian participation in DUMAN was strong at this time and continued strong until it was abruptly cut off by the Reagan administration. The severing of the Russian link was done with elegance and taste. We were told confidentially that while we were perfectly free to choose our collaborators as we liked, if perchance they included Russians, it would be found that no funding was available for us. So that, of course, was one of the reasons, but not the only one, that the Russian focus to their homeland deep water reservoir, which is Lake Baikal. Chudakov proposed to use Lake Baikal in 1980, and already 1 year later, site investigations started, led by Domogatsky and by Leonid Bezrukov. At the same time, the Russians were very active, and here we have Igor Zhelezny. He was certainly a key person of all that, exploiting the Atlantic, the Black Sea, the Indian Ocean, the Pacific and the Mediterranean side. There is a poster which I recommend you to look to. Now, the project which finally led to a working detector was in Lake Baikal and is in Lake Baikal, where you have at the deepest site 1.7 kilometers, and the site where the detector finally was deployed has a depth of 1.3 kilometer. And the advantage is that the lake is frozen in winter, so in late winter you have 8 weeks or 7 weeks. In the meantime, it's only 6 weeks due to climate change. Where you can go to the ice and you can drill holes and you can deploy your components. And then you have a cable to shore and it works over the year. And the next year you can even haul up components which have failed, repair them, and so on. So it's very, very convenient. A little less convenient is the fact that it is a lake with a limited depth. So 1.3 kilometers certainly not as good as 3 or 4 kilometers. So the Russians deployed 84, a first stationary string, not just from a boat for a few hours, but really stationary, and measured the muon flux. In 87, there was a second string where they got limits on gut magnetic monopoles, and all that they did with a rather old-fashioned 15 centimeter flat photomultiplier, and that was then changed with the development of a Russian smart phototube, which was a follow-up of Philips phototube of the same kind, where you have photoelectrons accelerated to a small scintillator. The small scintillator makes light, and you have a strong amplification factor here on the first step, and then here is a small photomultiplier which detects this light. So it gave an excellent peak-to-valley ratio for 1 photoelectron signals. So then, and that was more or less the moment when we joined from DESY, or at that time it was not yet DESY, but Eastern Germany Academy of Science. In 88 we joined and also helped developing the design of this 8-string detector. The first what was deployed was a 3-string with very short strings, but 3 strings is already what you need for 3-dimensional reconstruction. And I remember, typically I wrote here, the email came from John Learned, but it came from Francis in his unbelievable way to coin memorable sentences. He sent me an email and said, "Congratulations for winning the 3-string race." And that was exactly the same time when Amanda was going to deploy the first 4 strings, and Dumont was on the way to deploy the first 3 strings in the Pacific Ocean. And a little bit later, we had the first 2 neutrino candidates. Today, that would be called a rather meager evidence to be a upgoing muon, but okay, that was as it was at that time. The first textbook neutrinos appeared soon later when we had 4 strings, and this event here has already 19 fired pairs of photomultipliers, and there was no doubt that this was an upward-going muon. And so at the end, 98, we had NT200 because the number of photomultipliers was 192, so close to 200. And that worked until something like 2012. So the summary on NT200 is it was a pioneering detector. It had the first 3-string array underwater, first detection of neutrinos with Markov's method, but it was small. It was, for an underwater detector, ridiculously small, only twice of super K. It had poor reliability, high failure rates, and so the final statistics of muon events was only close to 400. That has to be compared for many thousands for Amanda and Antares. But still, it was a certain time competitive with Amanda in searching for a diffuse flux for neutrinos by looking beyond the limits, beyond the borders of the geometrical borders of the array, which you can do very easily in water, but not as good in ice. And why that is so, I can tell you later. Well, the flux predictions, there were coming flux predictions in the 80s, and if you look to them from today, they are still extremely optimistic, but the range is extremely big. So that was a prediction from, I think that was 92 or something like that. You have here different sources. You have, at that time, we knew only one TeV gamma ray source. That was a Crab nebula. You have here the gamma flux at Earth, which for the most sources was an extrapolation of the Egret satellite, luminosity, and then you have different assumptions. You had here the assumptions that the neutrino to gamma ratio would be 1, and the positive assumption, and that was something which had to do with the cocoon sources where nothing but neutrinos could escape. You have here an assumption of neutrino to gamma ratio of 30, and of course if this would have been true, then of course Dumont 2 and Amanda would have seen the first sources without any difficulties. The more pessimistic assumptions, of course, would have given also for Amanda point sources, but of course much less than these here. So here's another prediction or composition of calculations from models for diffuse fluxes, and you see this here would be 200 events. Would have been 200 events in Dumont 2, or 500 to 1,000 events in Amanda, and so we would have detected easily for all these models with Amanda already the diffuse flux, which we did only with IceCube. So in the 90s, all these predictions were again revisited, and it became clear that underground detectors could only do something for very young supernovae, which bombard, the pulsar bombards from inside the shell, and that would be for some months as a signal. But all the other things would need a detector of the order of a cubic kilometer, and that was when Francis and John wrote this summary, high energy neutrino astronomy towards a 1 cubic kilometer detector. So the idea of a cubic kilometer detector was always with us. Also we hoped, of course, that we see already something with Amanda and later also with Antares. There have been two interesting bounds, and you see them on the next slide. This is here the energy, so this would be here a TeV, this would be a PeV, etc. And this is a logarithm of the flux multiplied with E squared, so an E over minus 2 source would give the horizontal line here. And we have here a bound which is absolutely, which stands 100%. This is just derived from the observation of low energy gamma rays, which if you have somewhere interactions of protons, you will also generate gamma rays, and they can cascade down, so at the end you do not see TeV gamma rays, but GeV gamma rays, and there was an upper limit from Egret observations. So this was rather strict, this limit, but there was a stricter limit by Waxman and Bacall, which was derived from the very highest part of the cosmic rays, 10 to the 18 to the and to 10 to the 20 electron volt, and assuming E over minus 2 spectra for the sources. And another model by Mannheim, Prothero, and Rachen assumed that there are not only E over minus 2 sources of the similar kind, but that there are a lot of different sources with different spectra, and then you could arrive at this a little bit less tight limit than Waxman-Bacall. By the way, here's also a prediction for the assumption that all high-energy cosmic rays are generated in gamma ray bursts, which we have included meanwhile with IceCube. So let me come now to Amanda. The first ideas about Amanda came up in '88 when Francis was contacted by a glaciologist, Zeller, his name, from Kansas. And was he a glaciologist or a radio person? I don't remember that, Francis. You certainly remember. He was a glaciologist, and he had heard about attempts of radio detection of neutrinos in Antarctic ice. And it became rather soon, it became clear to Francis and to Enrique Sass and to others that the threshold for radio detection would be rather high, so it would be better to try it optically. And optically, of course, then you would contact of course, John Learned, and that's what Francis did. And so they wrote this paper soon later after Francis, the same year. So 89, rather independently of this main line of action, two youngsters from Berkeley tried to measure the ice transparencies in existing boreholes at the South Pole. And then also 89 in Adelaide, several people met and proposed AMANDA, Antarctic Muon and Neutrino Detection Array. Then again, a little bit later, Bob Morse from Wisconsin went to Greenland, not to the South Pole, and deployed photomultiplier to measure the attenuation lengths at 200-meter depths. The result was a Nature publication 2 years later, 1 year later. And if you look to the abstract, you see already here again the square kilometer, which is envisaged. You see here the word AMANDA, and you see here that the absorption length is derived to be greater than 18 meters, which, by the way, is pessimistic. The absorption length is much bigger, but what is much lower than the original assumptions is the scattering length. So scattering in ice fakes a lower absorption length than it is in reality. So then in 93, 94, what was later called AMANDA A was deployed, 4 strings with a distance of 20 or 40 meters respectively. And when the first measurements were made, is it really? No. I should have 10 minutes, I would say, right? And when the first measurements of the travel time from the light from here to here were made, it turned out that it have not been 100 nanoseconds as it should be, but microseconds. And the solution to that was actually that there was this strong scattering. And the Russians had made measurements of the bubble concentration at the dependence of depths which have not been known to Francis at that time. He repeatedly said if he would have known, then he never would have started AMANDA. But the good thing is the concentration of bubbles decreased with depths, and the same did our scattering length data. So that was encouragement to try it again at deeper depths. Still, that was a time when only idiots would have joined AMANDA, who have not yet been, and one of the idiots have been me, following Francis' repeated statement that the photomultipliers are working like switch watches. And but still, many people said, Leo Resvanes said, your detector is nothing but a big calorimeter. And there was this wonderful conference or a workshop where Vic Stenger from Dumont took the overhead projector, pointed it to the white wall and said, this is what AMANDA sees. And only white diffuse light. And then Francis stood up and switched off the projector and said, this is what Dumont sees. So then the next step was to deploy a detector at bigger depths, between 1,000 and 1,500 meters, at what was called AMANDA B4, consisting at that time of 4 strings, and that allowed us to separate the first neutrinos, upward going muons. Then the next year we deployed 6 additional strings, so it was then called AMANDA B10 with this wonderful event, which called EVA event, because a PhD student from Stockholm named Eva has detected it. And then shortly later we had the second Nature publication, 2001. This, by the way, was called Peacock event, because Dennis Peacock from NSF was just in Madison when they have been detected these events on the screen, and that was a moment from when on we were rather sure that IceCube could be built. So then we had several other steps to which I do not go in detail. The one thing which I want to mention is that this looks easy, but in principle, but in reality, it's rather it's a rather hard job, because here you see the reconstructed cosine angle. So this is horizontal and this is vertically upward. This is what you expect from atmospheric neutrinos, and this is our data. And this is a Monte Carlo calculation for downward going muons, which are misreconstructed. So our data, firstly, do not correspond to the atmospheric, to the Corsica calculations, and secondly, are more than 2 orders above the atmospheric neutrinos. So what you have to do is, and that has to do with ice, with the scattering, and so you have to do a lot of procedures and cuts to end finally at the point where you really are consistent with the atmospheric neutrino expectation, and where only a little bit misreconstructed downward, in fact, downward going muons remain. And this is so you could have with these data then a sky map which had a purity of 90 or 95% neutrinos with an admixture of only 5% muons, downward going muons. So this is what from Amanda remained. We had these results. We had record limits. We have measurement about atmospheric neutrinos until energies to which before nobody has measured them. But at the end, of course, it's essentially negative results, which we actually 6,500 muon neutrinos, which we have registered with Amanda in 7 years. Then the Mediterranean activities had 3 sites: Antares close to Toulon, Nemo close to Sicily, and Nestor close to Greece. And the first was Nestor, where the people had tower structures. They wanted to have at the end several towers with a total volume of 10.5 cubic meters, so only a tenth of a cubic kilometer. The first site studies have been done by Russians, again by Igor Zheleznych and by Leo Resvanes. Then they had a first hexagonal structure deployed in '91, first muon count, many ocean tests. They built laboratories and infrastructures. Then in 2000 they laid a cable to the site. Then they deployed the first floor, which failed after a few weeks. They got data. They got muon angular distributions, but the cable failed, and then it never was working again since then. Antares formed a little bit later. Some of the people who have been in, some of the French people who have been in Nestor split away from Nestor and formed their own collaboration. The first proposal for Antares was written in '99, and then over several years, this detector consisting of 12 lines has been installed. That is about the same size like Amanda, but with a totally different systematics because it's water. Scattering is much smaller. Reconstruction is easier. Of course, you have bioluminescence, you have potassium-40 decays that makes it more difficult. But in principle, of course, water as a nearly non-scattering medium is better than ice. So the conclusions for Antares is this is the first proof of long-term reliable underwater data taking with high precision. Baikal was a pioneer, but it was certainly not a high precision and high reliably working instrument. 7,500 muon neutrino events, and I will come to some results below. So Nemo, I will skip that, or not totally skip that. That was an attempt to do something close to Sicily. And these attempts are now part of KM3net. So IceCube, everybody of you know this picture. I do not have to go into details. Just to remind you the timeline, the first proposal was made in '99. We started construction in 2004. The last, the 86 string, was deployed in 2010. And we already record not 1,000 neutrinos per year, but 100,000 neutrinos per year. So that's a really new quality. The uptime is about or even bigger than 99.5%. In this week, where we live now, it is 99.9%, which of course is an exception, but typically is a set. So that's really a wonderful reliability, and the DOM failure rate, the digital optical modules, they fail with a rate of about 1 per year. So from that point of view, we could operate the detector several hundred years. Of course, NSF would not give us money for the maintenance and operation. So let me come to an end and just tell you where we stand. I think Francis will have something like this in his slides also. Here you see the so-called high energy starting events, which have been recorded with IceCube. Events which start in the detector, where you can be sure, even if they come from up and going down, that these are neutrinos. You can be nearly sure, of course, it's a mixture of misreconstructed muons or something else. And you see here the excess of what we have measured compared to what we expect from atmospheric neutrinos and from misreconstructed downgoing muons. And the uncertainty here has to do with the charm production and with the so-called prompt neutrinos. And these here are Ernie and Bird, which you all have heard about, and this is Big Bird at 2 PeV. And also Antares, meanwhile, has seen such an excess. You see here track events and shower events versus energy, and you see here an excess. It's only 1.6 sigma, but the flux which they derive is in agreement with the IceCube flux. So it's going to be seen also on the other hemisphere. We have also a lot of wonderful through-going muons. This is an event where we have a deposition of 2.6 PeV in the detector. So the estimated energy of the neutrino which has generated this event is 7 to 9 PeV. And this is actually the highest energy event we have. And so at the end, we have here fluxes on which we have derived in dependence on energy. Again, fluxes from these Hazer analysis with a contained event, and here from muons, upgoing muons for 6 years. And if you compare that to the flux predictions which I have shown a little bit earlier, you see here that we are indeed below these Waxman and Bacall bound. Of course, we could not be above it, but that we are so shortly below is really a lucky coincidence. It could have been lower. We did not know when we constructed IceCube for 100% that we would see extraterrestrial neutrinos. So again, repeating a sentence of Francis: nothing is guaranteed, but history is on our side, right? So history was on our side, and we have detected this flux. Search for steady point sources. I just show this picture here with Antares limits. These are all limits, and with limits under different assumptions about the cutoff for IceCube. Here would be no cutoff. Here would be a cutoff at 100 TeV. But what I want to transport with this slide is that from Amanda 2000 to IceCube now, we moved by a factor of 3,000 in sensitivity. So that is, by its own, I think, a fantastic success. And this is the last thing Francis will talk about, that this is the event which we have seen at September of last year, where several observatories from gamma rays to TeV observatories, from GeV to TeV gamma rays and optical and radio observatories have seen an enhanced flux from this object, which is a blazar named TXS 0506 plus 056, which is 5 billion light years away. And when we look to our archive data, we saw a 3.5 sigma neutrino. It's certainly not what you would call a clear discovery with 5 sigma, but everybody fits so well that if you would ask me, do you believe it? I mean, we had that now several times. I would say I believe it, but I would not say it's a discovery. So this is really my last summary slide. We had a long way, a really long way, starting in, technologically starting in '73, with tremendous challenges. The flux predictions went from uncertain to low. The way was long and thorny, but it was also not without fun, I would say. The method was proposed in '60, then the first steps towards Dumont in '73. The first neutrinos underwater in 93 and 96 by Amanda. 2008, the first undersea detector, Antares, then the first cubic kilometer ice cube, detection of a diffuse extraterrestrial flux of neutrinos in 2013. And what I should also mention, since 2014, even 13, we have a very strong alerted multi-messenger program, both in Antares and IceCube. And at the end, this led to the identification of these TXS source. And the next steps are Baikal gigaton volume detector, KM3net, and IceCube generation 2. And maybe, Francis, you have something about that. I want to limit myself to history here. Good, thank you.
Thank you, Christian, for this overview of the high energy end of the neutrino spectrum. Are there questions to Christian?
Well, of course I have to comment, but the comments I want to make are more in the spirit of the meeting of the history and culture and so on. It's a great summary of the history. One of the things that I thought was interesting was that in the 70s, when we first started talking about the really high energy neutrinos, nobody believed in neutrinos up in this energy range. And many people warned us off and said, don't design an experiment for 10 to the 16th EV and so on. It's not credible to think about it. And so Berezinski and Zatsepin, who were real pioneers in this and others, but they were not taken seriously with those predictions. Another thing had to do with the techniques that we were proposing.
Excuse me, John, may I ask you one question?
Yeah.
I mean, Berezinski and Zatsepin talking about GZK or Berezinski-Zatsepin neutrinos, that is one thing. The so-called astrophysical neutrinos, which are in the TeV, PeV region, is another thing.
Yeah, but people had no model for those sort of energies at that time.
So what led you to 1 cubic kilometer in your first dreams?
Well, we knew that we had rough estimates of the rates, and it's something. There was a nice argument. I think Francis used to use it, a simple numerical argument that leads you to that. But at any rate, that number has bounced back many times. So the other thing I wanted to say was that we also knew about all these different techniques other than optical detection. And again, for cultural reasons, we shied away from them and we went to the boring, simple technique with old optical detectors to start pursuing in the field, whereas people here may know that the electromagnetic, the Cherenkov goes as Z squared, so you get a much bigger pulse. In acoustic detection, the pulse gets much better with energy and so on. Some of these things scaled up so that you only could get into the business if you really were at the high energy regime. So we were frightened off and we started aiming at optical detectors at lower energies. Another cultural comment about being at the right time in the right place is in dear old Dumand, one of the problems we had was that the Department of Energy was totally unused to funding big experiments not at the accelerators. And so we always had reviews of committees, honest to God, this is amazing. The committees composed of accelerator physicists, high energy physicists, who had never been to sea, had never been involved in experiments in the out of doors. And while our oceanographer friends were saying, you guys are real heroes, you're mounting this amazing thing in the ocean. And yes, you have to fail 3 or 4 times before it will work. And the DOE guys are going, well, this is not acceptable.
Could you comment a little bit on the comparisons in terms of absorption length, not so much scattering? Because I realize that there is one aspect that people have a hard time to believe is that if you compare the water properties in the lake, Baikal, that is known to be so pure water and so beautiful place, it's actually much more, the absorption is much greater than in the deep sea. And every time I mention that, people have a hard time believing it. So do you confirm? And do you know what are the fundamental reasons for that?
Actually, I do not know the fundamental reasons. Of course, you have a little bit more biomatter, but that would at the same time also lead to more scattering. I know that it is 20 to 22 meters compared to the ocean where it is 40 to 50 meters, and compared to the ice where it is about 100 meters, a little bit depending on depths. I don't know the reasons.
I can comment on that. So in Baikal, there also is, because the stream's washing down into the lake, there's glacial dust and so on absorbed, and then there was a time-dependent background which changed with the season, and that people said was maybe tribal luminescence. I don't know how it all's worked out, but I want to make a comment about the optics that's sort of fun. One of the big problems we had, we used to fight about the difference between water and ice and so on. And one thing in common was that the people in the optics business all said that we were crazy, because measuring the optical transmission length and scattering length in water in the laboratory in cells this long, they said, well, tens of meters attenuation length is not right. And we had this in IMB in the early days. We measured the attenuation length in this ultra pure water, and we're getting, I've forgotten what, John, 50 meters or something like that. And the professionals in the business say, oh, this is nonsense. These people don't know what they're doing.
And the same they said, of course, when we measured 100-meter attenuation lengths in glacial ice. The only comment I want to make to your comment, it cannot be something which glaciers wash into the lake, because then we would have seasonal variation, which we have for scattering, but not for absorption.
You did not mention the radio and acoustic detection. Can you say a few words about this?
Well, I mean, as John said, they have been invented, conceived already during the Dumont workshops, and John is a pioneer of the in particular of the acoustic detection, where he made the first calculations how the release. So you have an ionization, you have a local heating from a cascade, not from a muon, that would not be enough, from a cascade, about 20 meters long, and then you generate from that a shock wave, which goes vertical, horizontal, which goes. Okay, if this is a cascade, it would go in that way, and then the question, of course, is how much sound. I don't know the words. Sound energy you would have for a certain energy of cascade, and they have, and I know there have been very different estimates, and one of them comes from you, one of the earliest one comes from you, and the other thing, the radio detection technique, that is something which Igor followed very intensively, and which now culminated in a sense in detectors at the South Pole. It is firstly ANITA, which looks to radio signals circulating around the South Pole from radio signals which have been generated in the ice. And on the other hand, it are the surface arrays Ariana at the shelf ice, and ARA at the South Pole. I think in the meantime, everybody is aware that the detector would be built at the South Pole. The question is still which technology, that of Ariana or that of ARA. And that will be an array which indeed will complement ice cube generation 2 towards higher energies. It's
with correlations between?
Yeah, they are exactly at the same place, and of course you can correlate the events.
Okay, if not, we break for coffee now and come back at 4 o'clock.